Welcome back to quantum mechanics. Today, we're going to be talking about angular momentum. That's right, not the classical angular momentum, although we will be looking at it for a bit just to get a general intuition on what quantum angular momentum really means. So, what is this lecture going to be about? Well, first we're going to discuss angular momentum in classical mechanics, then bring the concept over to quantum mechanics, explain what we actually need angular momentum for in quantum mechanics, and finally, we're going to be pursuing the first important part. Momentum, as you may recall, is an operator in quantum mechanics. And in our new three-dimensional framework, we can find eigenstates and eigenfunctions of that operator that tell us actual physical things about an object. However, those ones really aren't that interesting. Finding the eigenstates and eigenfunctions of the momentum operator by itself is pretty boring. However, things do get spicy when we come to look at the angular momentum operator. So, how does it look? Well, let's get a little glimpse by starting with classical angular momentum. Now, hopefully, you already know what angular momentum is. We start with an object rotating around some center. Now, in the most standard form of rotation, circular rotation, you'll notice that at any point in the rotation, the radial vector, or the position vector, is exactly perpendicular to the momentum vector. That's just how circles tend to work. Any tangent line will always be exactly perpendicular to the line connecting the point of tangency and the center. So, in these cases, it's natural to just set L is equal to mvr. This is probably the definition you're most familiar with, maybe the only definition you're familiar with. L is equal to mvr or m omega squared r if you want to use angular velocity instead of standard velocity or tangential velocity. But of course, this changes significantly when we leave the form of a circular orbit. Already, if we instead take some elliptical orbit, things don't become as nice. Angular velocity does not actually exactly correspond to mvr. It's more mvr sine theta, where theta is the angle between radius, or the radial vector, and the momentum. Of course, that's always equal to 1 if the radial vector and the momentum vector are always perpendicular, so that's why you don't see it in the circle equation. But when that's not true, like when we're dealing with an ellipse, it's true at these 4 points specifically. But if you take this point, for example, the momentum vector is definitely not perpendicular to the radial vector. So when you change the orbit shape up, sine theta now actually becomes something that can be factored in. But here's the real kicker. This only, let's not pull it up that way. The real kicker is what happens when you try to turn things from 2D to 3D. Let's take, for example, the spherical pendulum, which is just an object in three-dimensional space that is given some initial position and velocity, and that is free to move around the 3D sphere, with its only limitation being gravity, and of course the length of the string, not allowing it to go closer or farther from the center. So, in this case, as you can see, its plane of rotation is constantly changing, which means that at two completely different points in the object's trajectory, everything about it, from the angular velocity to the angular acceleration to the angular momentum, could be the same, and yet the situation of these two is totally different because of the way gravity acts on them. So that means that we have to figure out some way to express the plane of rotation for these guys too. And the easiest way to do that is just to, well, how do we ever associate a plane with a vector? Well, we can just pick its perpendicular. It's not worth it to try and look for the vector that's encompassed by the plane, because the vector encompasses two vectors as well as the span of the two vectors that generate it. So it's pointless trying to look for the singular vector that encompasses the entire plane, but there is one singular vector, and of course all of its scalar multiples, but there's one singular direction that is exactly perpendicular to this plane. And let's set that to be the direction of omega, alpha, L, all the funky angular quantities. So that means L is equal to mvp, oh sorry, not mvp, that's not, mvr sine theta, that's just the magnitude, and the direction is just outward from the plane that contains both the radius and momentum. Wait a minute. Wouldn't that just make L equal to mv cross r? Or by associativity, p cross r? And that is the exact definition of angular momentum that we transfer over into quantum mechanics. Remember, we don't really have a concept of angles and stuff yet. Circular motion doesn't make much sense in quantum mechanics yet. So all we're going to use is L is equal to P cross R. Now, how do we work with that? Well, I don't remember the cross product formula, so I'm going to do the old trick where you take the determinant of a certain 3x3 matrix, where you have unit vectors on top, and yes, this isn't really a matrix, but because the determinant of a 3x3 matrix can be calculated in the same manner, it's an easy way to go about things. Px, py, pz, x, y, z, and then you use the mnemonic for calculating the determinant of a matrix. So you get the first component is zpy, and I think I can do the rest from here, minus ypz. The second component is probably going to be, actually no, probably. So pzx, or xpz, minus zpx. And the last term is going to be ypx minus xpy. So in total, we get that Lx is equal to zpy minus ypz. Ly is equal to xpz minus zpx. And Lz is equal to ypx minus xpy. Now what can we do? Well, here's the good thing. We know we already have the definition of momentum as an operator in quantum mechanics. Momentum in some direction is just equal to minus IH bar times the partial derivative of whatever comes after it in said direction. Remember, momentum is an operator. Right now, it doesn't make sense by itself. It only makes sense when it's applied to the wave function or some other function. And then that also allows you to find the eigenstates, which actually allow you to talk about the momentum and position of an object. Think about these not as actual momentum, but as a tool for you to find the actual momentum of an object. Because this by itself doesn't make any sense at all when you call it momentum. It's the momentum operator. an operator that, when applied to the wave function, helps you extract the momentum. So now, what happens when we plug this in? Well, we get Lx is equal to, if we factor out the minus I h bar in advance, this becomes a lot easier to process. Z partial y minus y partial z. Ly is equal to minus I h bar x partial z minus z partial x. And Lz is equal to minus I h bar y partial x minus x partial y. Here we go. So, once that's done, well, what else do we have to do? Now that we've defined angular momentum's components as quantum operators in their own right, we have to test if they're actually compatible with one another. Now, what does it mean to be compatible? Well, recall that by Heisenberg's uncertainty principle, if you have two quantities with their A and B with their associated operators, then the standard deviation, i.e. reliability, with which you can measure them, their reliability always has to be worse than some specific quantity. In the case of position and momentum, happen to be h bar over 2. But in general, it's 1 over 2i multiplied by the commutator of their related operators. So, what is the commutator of, let's say, two of these guys? And first of all, why do we call two operators with zero commutators compatible quantities? Well, because if there's no ambiguity in measurement, we can always measure both with arbitrary accuracy. We can increase precision on one without losing precision on the other. Then that means we are allowed to find eigenstates that are consistent, perfectly consistent with both quantities. Now, quantum reality brings us the unfortunate Quantum mechanics brings us the unfortunate reality that not everything can be perfectly measured and known. In fact, some things probably don't even exist until they're measured, and their measurements aren't completely reliable. So, that makes things a lot more difficult than in classical mechanics. But we have to stay working. We can only know eigenstates of two different things at the same time if they're compatible, i.e. if they're both measurable at once. If we can measure one without losing track of the other. Wow, I've repeated that a lot of times by this point. So now let's test if Lx and Ly are compatible. And then we can obtain the rest by cyclic permutation to get yz and zx. And for the other three pairs, like xz, zy, and yx, all you have to do is just flip the sign. That's how commutators work. So, what is the commutator of Lx and Ly? That's going to take a while. And first, you have to apply it to a test function. That's what happens anytime we try to work with operators. Because operators have almost no meaning by themselves. They have to be applied to a function for us to actually do anything with them. So, what's the commutator of these guys multiplied by f? Well, it's Lx Lyf minus Ly Lxf. And then, what's this? Well, you have to expand it into, well, what's Lx and Ly? Lx is First, we have to factor out the minus I h bar squared. So we'll just leave that over there. And then everything else is going to be, well, Lx is z partial y multiplied by, and then you have Ly, which is x partial yf minus y, no, x partial zf. Z partial xf. And then you have minus y partial z times x partial zf minus z partial xf. Okay. So this is just the first term. Minus the second term is going to be, so let's see. Minus Ly Lxf, so that's just going to be everything in reverse order. X partial z, z partial y, f. Ow. My handwriting's hopefully going to get much better now that I can actually write this way. There is no way for me to continue. Plus z partial x, z partial y, f minus y partial z. Okay, here we go. Now, the next step is to actually simplify that more. What else did you think it was going to be? Actually, we have more space here. Let's use it. So, what happens when we try to reduce this down? Well, first we have to abuse the chain rule and the product rule. So we get z multiplied by, and we get partial y of, oh boy, I'll just go through it myself and you can verify this. So partial y partial zf, which is going to be fyz, minus partial yz partial xf, so that's going to be minus, oh sorry, this should be x fyz minus z f xy, and then minus y, once we distribute the partial z, that's going to become x fzz minus partial xf, or fx, minus z fxz minus x, and then we distribute that, and that's going to become partial yf plus z, okay, that's going to become fy fyz. Oh, and there's another term in there, minus y fzz plus z z fxy minus y fxz. There we go. So now let's try to condense that even more, right? So first things first, let's bring all the z terms together. So we're going to get minus x times fy plus z fyz minus y fzz minus y x fzz minus fx minus z fxz, and then you add the z terms together, and x fyz, oh sorry, minus z fxy canceled out with, no, so we have z times, where's the other z term? Oh man, here it is, So minus zfxy cancels out with zxfy, fxy, and we have left over xfyz minus yfxz. There we go. Okay. So then, what else is left over? Well, now let's refactor this. Factoring out fyz first, because that's the first thing I see here. We have xz minus xz, which means it disappears. Then the next thing I see is fxz. There's a minus yz term right there, and there's a plus yz term, or minus y times minus z. There's a plus yz term over there, so that also disappears. And then plus fzz, well, there's a xy term over there, and there's a minus yx term over there, so that also disappears. And, well, everything else is minus xfy and yfx. So it's yfx minus xfy. So at the end, of the day, the commutator of lx ly times f ended up being equal to minus I8 bar squared times, I know, I'm just trying to write an important result. Y partial xf minus x partial yf. There we go. So now, what do we do with this? Well, you probably have noticed that this looks very similar to, if we eliminate the f, that makes it look more like this, which is very similar to LZ, which is just minus IH bar times y partial x minus x partial y. So, well, what are we left with? We should get minus IH bar LZ. There's a sign error here because I'm supposed to be getting IH bar LZ, but whatever. So, by cyclic permutation, you can probably realize that the commutator of LY-LZ is going to be IH bar LX, and LZ-LX is going to be IH bar LY. Alright, now we're just getting started. So, don't want to crack my fingernails. So, over here now, we're going to realize that this means LX and LY, well, the standard deviations of them, when we measure them, they're going to have to be at least, their product is going to have to be at least 1 over 2i multiplied by minus IH. No, it's not minus. Oh, sorry, yeah. So it's going to be equal to the absolute value of 1 over 2i minus IH bar LZ. So, at the end of the day, it's saying that it's going to be greater than or equal to h bar over 2 LZ. Oops. So that means that these two are not compatible. And the same thing happens with Ly and LZ. They are going to have to be greater than or equal to h bar over 2 LX. So, and we'll see soon the intuitive reason why if LZ is equal to 0, we can perfectly know both LX and LY very well. 2D things are always the best, except for life. Life is better than 3D. So, now, we want to search for something that is compatible. And the natural next best guess is, what about the magnitude? But of course, the magnitude by itself is messy. What does it even mean to take the square root of a bunch of operators? So instead, we take the magnitude squared. That doesn't even require any simplification. It's just Lx squared, that makes sense. Ly squared, that makes sense. Lz squared, that makes sense. It's a lot easier to deal with integer powers than with fractional powers of operators. just look at how difficult it is to define a fractional derivative and get back to it. So, does this commute with anything? Well, let's try it with Lx. Since angular momentum, being proportional to angular position, happens to be, since angular momentum, being proportional to regular momentum, happens to be a linear operator, regular momentum at the end of the day is just a partial derivative times a constant, is a linear operator, which means that we can take this and break it up into Lx squared Lx, Ly squared Lx, and Lz squared Lx. Now this is going to go to 0, since if you really think about it, this is just Lx cubed minus Lx cubed. What is this going to give you? Well, it's Ly squared Lx minus Lx Ly squared. And the same thing with this, it's going to be Lz squared Lx minus Lx Lz squared. Now realize that when you have something like this, you can always break it up into Ly Lx plus Ly Lx Ly. Just look at what happens when we plug this back in. We get Ly Lx minus Lx Ly. So there's Ly squared Lx, and there's a minus Ly Lx Ly. And over here, we're going to get plus Ly Lx minus Lx Ly Ly. And so the Ly Lx Ly term from over here cancels out with the positive one over here. And all we're left with is Ly squared Lx minus Lx Ly squared. So, trust this formula. And now that we have this, all we have to do is plug in what we already know about the commutators. This is going to give us since this is actually in the flipped order, Lx Ly is supposed to be I h bar Lz. This in reversed order is minus I h bar Lz. Then over here, well, these commute. You get minus I h bar. Wait, no, these don't commute. Sorry. Ly and Lz don't commute unless Lx is equal to 0. That's a whole business that we've been talking about for a while now. So, we have that this is minus Lz minus IH times IH bar Ly. Why? Because LZ-LX is in the right order this time. This is LZ-LX. And since this is in the right order, we don't need to flip the sign. This is just IH bar Ly plus IH bar Ly LX. Oh, sorry, LZ. So, LZ, Ly cancels out with this, and LZ, IH bar Ly cancels out with, no, that's not true. LZ, Ly cancels out this way, since you have LZ, Ly here, LZ, Ly here, and Ly, LZ cancels out with the other Ly, LZ. So, in the end of the day, no matter which way the cookie crumbles, this is all equal to 0. Which means that, bicyclic permutation, the magnitude of L squared always commutes with any component of the angular momentum, which is great. These two are compatible, which means we can find simultaneous eigenstates for them. So, let's do that. How do we find simultaneous eigenstates? Well, first of all, what is an eigenstate? Recall that, well, an eigenstate is just a pair of an eigenvalue and an eigenfunction. And recall that all we are doing is taking the operator multiplying it by a function, and seeing for what specific function and scalar this can be true. So to do that, well, it's going to be extremely impractical to start from the function or from the scalar. What we're going to do is assume we've already found some solution to this, ft and lambda. And, or let's not even call it ft. Let's call it f. Let's just call it f. And so, here's what I'm going to do. We're going to take the ladder operator approach that we used a long time ago to solve the time-independent Schrodinger equation for possible wave functions. So how are we going to go about it this way? Well, let's define the ladder operator. L plus is equal to Lx plus ILy, and the other way around. Now, you can probably tell, hopefully, that both of these commute with a norm of L squared. Check and check. Since, of course, this is a linear operator, and this is just a linear sum of Lx and a constant times Ly. So that's pretty easy peasy so far. Now, how do we proceed with actually finding the eigenvalues? Well, so we're going to start with L squared, which is Lx squared plus Ly squared plus Lz squared. F is equal to lambda f for some f. Now, we're going to call, and actually let's call it f naught, as 0 is cool. We're going to say L plus multiplied by f naught is equal to f1. And we're going to say L minus is going to be equal to f minus 1. Now, I am going to claim that f1 is also an eigenfunction of both L's norm and L, let's pick a component, Lx. So, the magnitude of L squared multiplied by f is equal to lambda f naught. Then, this squared f1 is equal to what? F1. This has to be a scalar, otherwise we failed. So the norm squared multiplied by Lx plus ILy is equal to, what is this? Well, we don't know. Let's call it, I'm going to put this as lambda naught. Let's call it lambda 1. So, f1 is just, so this is f0. f1 is just Lx plus ILy, f0. And before you think about canceling things out, not so fast. We can't just run over and do that. What we can do is realize that since L norm squared commutes with Lx and it commutes with Ly, actually we've already used Lx and Ly. I think I should probably pick Lz to avoid compatibility issues. So this already commutes with Lx and it commutes with Ly. So we are totally free to write that, let's distribute, we get Lx times Lx squared plus Ly squared plus Lz squared plus Ly times Lx squared plus Ly squared plus Lz squared is f naught is equal to lambda 1 Lx plus I Ly f naught. So now, how do we find lambda 1 here? Well, since L squared still commutes with L plus and it commutes with L minus, we are allowed to just take this and shuffle it. We are allowed to take this and shuffle it over behind a lambda 1, because operators like these always commute with constants. And we are allowed to take this and shuffle it over behind L squared, because these two commute. Which means we're allowed to take L plus L squared f naught is equal to L plus lambda 1 f naught. And well, that makes it pretty obvious that L squared f naught is equal to lambda 1 f naught. And so that means lambda 1 has to be equal to lambda naught. That simple, right? But now let's look at LZ. We know that LZ doesn't commute with L plus or L minus. So what happens when we take that? Will f1 still be an eigenfunction? And will lambda 1 still be an eigenvalue? Well, let's take a look. It should be immediately obvious that lambda 1 will not be an eigenvalue, since these two don't commute. But is f1 still an eigenfunction? That also seems unlikely. But we have to actually figure it out. Functions aren't as intuitive as we always think they are. So we take LZ f1 is equal to lambda 1. No, we can't use lambda 1. Let's use lambda 1 over line f naught. Well, the past usage of lambda 1 had us discover that lambda 1 was actually equal to lambda 0. So lambda 0 is going to be reserved for all of these little guys. Lambda 1 is going to be reserved for the new exciting eigenvalue that will hopefully come out of this. So what happens here? Well, this becomes LZ L plus f1 is equal to lambda 1 L plus this should be f naught. Now we shuffle this behind, which still works, and we shuffle this behind, but that comes with a cost, you see, because we know that LZ L plus is not equal to L plus LZ. We actually want to find the commutator of LZ L plus. Of course, that's just going to be the commutator of LZ Lx plus I LZ Ly. And so that's going to give us I h bar Ly. This is in the wrong order, which means we have to flip the sign. This is going to be minus I squared, which is just going to make it plus again, I h bar Lx. So it's just going to be I h bar Lx plus Ly. That's the commutator, which means that this is equal to L plus LZ f naught, but plus what? Well, LZ L plus f naught minus L plus LZ f naught is equal to I h bar Lx plus Ly f naught. Which implies that, well, when bringing it over to this side, we're just going to get I h bar Lx plus Ly f naught. There we go. So now we figure out that here lambda 1 has to be equal to lambda 0 plus h bar. So there. And by yourself you can figure out that lambda minus 1 is equal to lambda 0 minus h bar. I don't feel like doing that right now. So we have constructed a ladder, just like we did with the time-independent equation so long ago. A ladder of eigenfunctions and eigenvalues. So plus h bar times L plus. And of course, you can go down the ladder too. And you will probably realize that just like the time-independent Schrodinger equation, you are bound to hit the bottom rung. But what you might not realize is that unlike the time-independent Schrodinger equation, there is also a top rung. Why? How can we calculate them? And how does this allow us to calculate the eigenvalues? When are we calculating the eigenfunctions? Well, this is what we're going to be talking about next time. This is what we're going to be talking about next